Hello, everyone. My name is Megan Carter, and I'm ESIP's Community Director, and I'm delighted to welcome you today to the next installment in the 2021 Earth Science Information Partners Innovation Webinar Series, which follows our 2021 year theme of Leading Innovation in Earth Science Data Frontiers. We're delighted today to welcome today's speakers, Keith Mall, data scientist and software engineer at the Research Library at NCAR, and Agbeli Amico, associate scientist also at NCAR in the Computational and Information Systems Lab. So if you're not familiar with ESIP, I'll give you just a very quick introduction. ESIP strives to be a leader in promoting the collection, stewardship, use and reuse of earth science data, information, and knowledge, and to be responsive to societal needs. So for more than 20 years now, we've been helping members of the earth science data community to find each other and to work together on common data challenges, to leverage each other's expertise to solve problems at their home institutions, to really bring real solutions back to their home institutions. In order to help earth science data professionals in this way, we foster a number of rich collaborative experiences, which include numerous community-driven virtual collaborations, the ESIP Lab, which supports the development of innovative applied earth science technologies. And we also hold 2 annual conferences. And the next meeting will be in January. It will be fully virtual. And our agenda will include 30+ community contributed breakout sessions on a wide range of topics such as data stewardship, geosemantics, cloud computing, AI, machine learning, as well as multiple plenaries and numerous networking opportunities. We encourage you to join us for the meeting and to consider submitting a session for to the call for sessions, which is now out, due November 8th. And you'll see in this graphic on the bottom right that the theme for the meeting is data for all people, from generation to use and understanding. So now moving on to today's webinar. Again, we're excited to welcome Keith and Ag here today. I'll give a brief bio for each of them and then we'll pass it over to them. Keith Mall is a data scientist and software engineer in the Research Library at NCAR in Boulder, Colorado. His core research lies at the intersection of scholarly metrics, research impact, and research traceability. Recently, however, he has been expanding his work into strategies to understand how Internet of Things data platforms, education, and citizen science might improve the impact of scientific research, where the data exists by empowering the communities to be full participants. Keith holds a PhD in computer science from the University of Colorado Boulder. Agbeli Amico has 20 years of experience in commercial weather forecasting, international business development, renewable energy, sensors, and data science. Ag is working at NCAR's Computational and Information Systems Lab, specifically working on user-friendly 3D printed weather station platforms using Raspberry Pi embedded weather forecasting for use in education, outreach, and field programs. He enjoys training for and participating in ultramarathons, ski mountaineering, and ocean races in fun places around the world. Those are some fun facts. So without any further ado, I will pass it on to our speakers. We will have time, by the way, for questions at the end of the presentations. And also I should note, you will likely have already realized this, that we are recording this session and we'll be sharing this on YouTube following the webinar.
All right, thank you so much, Megan. Screen's good, everything's in good shape, so.
Looks great.
All right, so thanks again for the invite. We're always excited and delighted to, engage with ESIP. And in fact, we'll talk a little bit more about how, through this presentation, how this work evolved in one way because of ESIP. So we'll talk about 3D printed weather stations and, sort of these 3 axes along sort of education, citizen science, and research. We'll give a little bit of a background about what the project is all about and, the parts of the project that we, are trying to evolve at this point. And then we'll have some discussion. Ag and I will sort of tag team back and forth, sort of midpoint and switch. So, but we will have a good session nonetheless. So let's get going, I guess. Let's see. Okay, so let's talk a little bit about 3D printed weather stations. Most of the audience, I'm going to guess, has at least some exposure to maybe the inexpensive weather stations that you could purchase, say, at your local hardware store. And in some cases, some department stores like Target probably have these, something under $100 that may have a little display and give some pretty interesting output. But most of the time, when they break, people will go and just get another one, right? And we know that weather stations are a sort of necessary component to, and a lot of people like that weather station because it's real time and it's fun and you sort of see what the temperature is. But we know that a lot of what we're getting today, would sort of feed into something bigger, right? Whether that be for historical data capture or for prediction and modeling. And so this idea about how do you take that concept of a weather station that is inexpensive, but one that you might be able to build yourself is kind of at the core of the work that we're doing. And so, we've recognized that these weather stations exist and they're inexpensive, but, most of them are not hackable, even though, if you try hard enough, you can probably hack into some of them. But there are lots of different use cases that, we might be able to open up if a platform is designed and developed that allowed a larger community to contribute. So, what we're trying to really do is take sort of the best ideas that are emerging out of IoT platforms, look at what's going on in the 3D printing realm, which at this point you can get a very good 3D printer for around $200, and then merge that with some of the really amazing things that are happening in communication technology, either low cost and sort of low power communication, as well as microprocessor technology, where we're looking at $8 microcontrollers with Wi-Fi and Bluetooth built in that you could, flash in a matter of minutes and have them do some pretty cool things. We're also, of course, really interested in sort of low cost and making sure things are open source. And as I said before, one of the major concepts that we're trying to infuse in this is, looking at this as sort of open, and soliciting community input, and in fact, in some ways, letting communities take things in directions that maybe we would never think about on their own. So the idea behind our IoTwx platform is, we want open weather stations for everyone, everywhere. The kernel of the idea came from another project that was that preceded it here in UCAR with the 3D Pause project. Because some of you may be aware of 3D Pause. It is a very similar 3D printed weather station, except their platform is designed around a single SBC Raspberry Pi. And some of the changes that we made to that original architecture sort of broke things out into a more modular architecture, as well as a more plug and play one, where if we wanted to put this into a classroom, no soldering iron would be required, very low understanding of analog or digital electronics would be required. You could still get something done. There is another project called the Array of Things. This is a project that I think there were some collaborators from Northwestern and also University of Illinois. They had done some deployments originally, I think, in the city of Chicago. And, it's a very similar idea where developing a platform for urban measurement, so they were looking at putting platforms, say, on street corners, and you've got sensors for sound, and you got air quality sensors, et cetera. And that project, as far as I know, is still growing, but I don't know the status of what other cities they start to move into. But a very interesting project. If you are not familiar with it, you should take a look at it. But again, as I said before, we're really trying to support rapid development and try to use platforms that are easy to deploy and replace in some cases, and have the lowest cost for the highest benefit to the largest number of people. And in terms of where we, are kind of hoping to go with this, longer term, is that we would encourage educational, platforms that allow for a spectrum of activities around both data, software, and also looking at engineering. So if you really wanted to get down into building your own sensor, that is certainly within scope. So ESIP actually did fund us for sort of I think we actually still have a little bit left, so things have, we've done a pretty, I guess our budgeting has been pretty good, maybe. But in 2019, we had received a small startup grant to deploy these, sort of make some enhancements to the platform and deploy them into Puerto Rico. And kind of our overarching goals were to kind of reduce the learning curve, come up with some new communications mechanisms, possibly some new data storage mechanisms, reduce the number of parts, and make some things more available on GitHub. And of course, to make things faster to deploy, because at the end of the day, if we could get it down to after printing, you could have a station that was available and ready to deploy and be deployed within an hour. That would be wonderful. So what you're seeing is a picture of a prototype early on in the kind of first phase of our ESIP funding, where we were trying to come up with a slightly different mechanism for what we're calling the arrow node, which is a anemometer and a wind vane. So if we reimagine the weather station as sort of a set of interconnected nodes, and maybe the connection is wireless, potentially, this diagram kind of lays out, sort of the basic vision of what we're trying to accomplish. So if you have a set of nodes that are just basically controlled by a microcontroller that at some level would have a connection to some sort of wireless, either hotspot or a router of some sort, so that it could transmit its data. And then you could loosely call a weather station a collection of these nodes, where maybe each node, each microcontroller is responsible for one or more related sets of measurements. So the kind of fundamental shift in our thinking here was, let's see if we can maybe even shift the attention towards building a weather station in parts, so that maybe I could get one node up and running while I'm experimenting with another node, and maybe trying some new sensors out, or even trying a different 3D printed design for it. One of the main areas that we started thinking about this being as useful was in sort of reducing failure points, making sure that a node can maybe focus on a series of measurements that are all sort of related, which means that quite possibly it could perform some additional calculations and enhancements on this measurement before sending them off, but also being able to add nodes that are maybe full-blown machines, right? And so in the far right of this diagram, you see this IoTedge node, and this is a Jetson Nano, which is an NVIDIA product that allows you to basically, get a rather substantial computer with some decent processing power in a very small package that you could, for example, run some relatively complex models in. Okay, so this just shows us a little bit of an example of one of the major areas that we spent our ESIP funds on to improve and make some major design enhancements to the anemometer one thing. So what we wanted to do was basically, I think probably the more interesting aspect of this particular design was that we decided to take a digital compass and use a digital compass as the wind vane and effectively spin the compass to determine the direction. And in doing that, we implemented that particular design change using a slip ring. And it turned out to be rather interesting and fun, and allowed us to also think about other digital sensors, digital compasses that we could implement in a very similar fashion. So it sort of opened up an entirely new way of thinking about how we might get those direction measurements. We are still, and we have a bullet point on here in terms of our solar power. We are still working on solar. One of our core concepts is to try to keep things in a reasonable and narrow, as narrowly defined as we can get it, budget constraint. And as many folks on the call probably already know, there are, once you get to a certain point, solar is still kind of expensive. And if we're trying to keep the entire platform below a certain cost and also allow it to be deployed in a lot of different places, solar may not necessarily be the best or least expensive. And we are also looking at other possibilities, like, for example, with wind power. Because we know, in some locations, solar will not be available for a good part of the year. Okay, so I'm going to hand off to Ag on this slide. He's going to take us through some very exciting things he's been working on the edge, and with a very interesting projects there. And then we'll pass back when he's done.
Thank you, Keith. Can everyone hear me okay? Good. So yeah, so one of the things next thing we're looking at is edge computing with the WRF, the Weather Research Forecast Modeling. So what we looked at is WRF on the Raspberry Pi, and this summer we added a Jupyter notebook front into the system. So as you can see here, the WRF model can run on, and it's sort of like a user-friendly way, and it can run on a single Raspberry Pi, or as you see in the picture here, it can run on a cluster of Raspberry Pis. At Sizzle, at Sizzle at NCAR, we have a scale model where we have 14 of these Raspberry Pis that look like and of course we have a 3D printed case over it that looks like the scale version of the supercomputer Cheyenne at the Wyoming Supercomputing Center. So, but the idea here is to figure out, okay, of course, we're getting a new cray, the derecho, so of course that's going to come with, a different shape. So we're kind of looking at, okay, how can we demonstrate parallelization, parallel modeling, weather forecast modeling, and demonstrate that on the Raspberry Pi or on a Jetson Nano would be coming up next. But what we did was we put a Jupyter notebook front into it so that it's easier for users to be able to make changes and develop their own notebooks. So for example, it spits, the model runs, you can change the initializations, or you can play with things like the GRIB files and be able to pull the GRIB files back in and do all kinds of different plottings and analysis on the GRIB files, or integrate those GRIB files directly into other code bases that you have on the Jupyter notebooks. So if you go to the next slide, one of the things that we've done with this, we've also created sort of teaching boxes, and this is sort of a website here that you can go to in the creation of the PyWolf teaching box that allows for you, when you download and clone that repo, you can make changes to the repo. You can basically create your own case studies or your own examples teaching various different concepts, and then you would be able to push those new concepts back up to and submit those to us after you've played with the teaching boxes. You can basically create your own teaching box and submit it back to us. Our initial teaching boxes have been written. Of course, you have Jupyter notebooks as part of the Raspberry Pi analysis on the front end, but then you also have Jupyter Book that allows you to write books in Markdown and write documentation in the Markdown and be able to submit that documentation to that. Now, going forward, creating this, what we're looking to do, of course, this is a community-driven thing. We only got a couple teaching boxes in the works right now, but we're working with other partners who I think will be adding teaching boxes in the future. But one of the other things we're looking at is creating boxes that merge IoT observation and modeling together. So if you have a station that, or a number of stations that can actually run WRF at the edge and create observation and feed those observations through data assimilation and assimilate that data into the models, then you start to have sort of the integration of smart computing, observation, and data assimilation through the modeling process, which is kind of where we're kind of thinking there. But right now, it's just at a really high level sort of educational form. But I think there's some real potential in that, and also tied to education of those concepts as well. And so, yeah, IoT, this can open up some really interesting case studies. And so some of the case studies is really some really cost-effective stations for research project support. And that's one of the things that we've really been looking at is, support lower cost deployments to help field studies. That's one of the things that I think is really important. Looking at incorporating IoT into different field programs, for high altitude, Arctic, Antarctic sort of extreme conditions. You can see being able to get and fill those data deserts where there are less density of field stations is something that would be that having a lower cost station would be able to achieve, and encourage new instrument design and deployment and sharing, I think is also good. Now, of course, there's the K16 plus education and training. That's been a part of the goal of some of the teaching boxes and the work that we've done with Raspberry Pi and with PyWRF and with IoTwx. And that is to support integration into classroom activities that meet NGSS standards, support so the school programs, maker spaces, and educational applications. At the college level, this is collaboration with MSIs, indigenous communities. We're working with a couple of different indigenous organizations and communities on integration into some of their programs right now. So those are some of the projects that we have underway, and they're sort of taking leadership role in working with our stations, developing it into a program that really fits the needs of the local indigenous communities. Of course, lastly, develop sort of undergraduate curriculum for data literacy, citizen science, and sort of decision support and analysis. And with the PyWRF integration, we can also start looking at advanced edge computing curriculum, and that's from data assimilation and modeling. And Keith, you're on mute, Keith.
Sorry about that. So I wanted to throw a little bit more detail around this idea of, these three axes that I talked about at the very beginning: this hardware axis, the software axis, and the data axis, and how we could envision a development of a lot of educational materials along each of these axes. And so, on the hardware side, you can sort of think about what it means to, for example, develop your own system. And this could actually be measurements by proxy, right? We don't have to have a complicated design to make a sensor, and you could start at something very simple and elementary and build that up. In addition, if you wanted to go complicated, though, right now we have 3D printed circuit boards, right? So for some universities that have that capability, you probably could implement a sensor design course or module in a course where you have undergraduate EE students develop their own sensor run the design through, go print that design, and then put it into a test mode on one of the stations. So, we are really seeing that hardware being a very exciting area, especially given where 3D printed PCBs are going at this point, and the speed with which they're becoming integrated into a lot of different things. On the software side, again, for the software folk on the call, you could clearly start to see the multitude of places you could go with software, from areas around updating and deploying the software on the microcontrollers, to the integration of management platforms. Right? So we had a student last year who was working on looking into the variety of IoT data management platforms, and what does that mean for individual community needs, whether they be open source IoT or for a closed source or whatever. And then there is this other thing about reliability, right? We've come to expect weather stations and these measurement devices to be highly reliable and highly stable. And when things don't go the way we expect or they go offline, we need to find out why. And so there's a really interesting software project or projects in that area. How do we boost the reliability of these very low cost devices? And then of course, I really don't need to talk to this particular crowd about the data side of this, but as Ag mentioned, we've been everyone wants to find a way to get Jupyter notebooks into the project, right? So we found a way to do that. But the civic engagement on the data level is also critically important. I think one of the areas that we are really trying to think about is how do we invoke concepts around data stewardship at the community level. As Ag mentioned, we are working with a couple of different communities right now, and that kind of conversation is coming up, especially around data sovereignty, right? And the concepts that we want to make sure that, for data that I want to share, and we would like everyone to share data, but not every data needs to be shared or wants to be shared. So, we need to, understand that and give everyone the ability to make whatever boundaries they need around the data, but also be encouraged to share that data in a way that other communities can benefit from. Okay, so in terms of sort of our base ESIP funded, component that was funded for this particular project and sort of where things are, our hydro node is complete at this point. The Atmos node, which basically does temperature, humidity, pressure, and we implemented a VOC sensor now, and that's now complete. We are still running into some issues around power and communication. Again, most of that is being held up by our pricing constraints. So finding very inexpensive ways to get as much power as we can to keep the system running for weeks. That presents some cost issues right now that we're still dealing with. And then in terms of our communications, we've been using a very lightweight protocol called MQTT, which is very popular in the IoT space. And that seems to be a great way for us to kind of get data where we need to get it very easily, and also do it, with as little power as possible. But we are still running into issues there that we're working through. But our Aero node, which is basically an anemometer and a wind vane, we've got a design complete, and we are still in the process of testing it. As Ag will talk in the next couple of slides, as we've been doing some field work with this, we're getting more and more information about some improvements that we may need to make, or some enhancements along those lines. But it's looking pretty good right now, and we still have a little bit of work to do on it. But that's how things are going in terms of the overall progress of our basic project. And so there are kind of two places you can go to get information. Our original ESIP funded Climate Change Explorer is the URL is listed here. And then we have for the work that we've been doing at NCAR, there's the equivalent manual over there. and some enhancements and some other things that may be of use and interest to people. And in that manual, we've and this was again driven by the funds that we got from ISIP. We put in some some simplified instructions with some really nice visual diagrams for construction of the individual nodes in the station. And I failed to mention at the very beginning that most of the connective tissue on the actual station itself is PVC. So all of our parts are sort of connected by way of PVC, but they do not have to be PVC. And of course, as we are always interested in interesting permutations to the design that we have, we're quite certain that there are other clever materials that people would use to stand up one of the stations. Okay, so Ag, I'll pass it over to you and have you give a little bit of a breakdown of our field stuff.
Yeah, so thank you, Keith. So we've been testing it in the field. And so you've seen there are a few sort of backyard tests. Of course, I have one right outside my spot here as well. And you can see there are different configurations. For the one on the far left, as you can see, is the full system with the aero node, hydro node attached as well. So you can see this middle one does not have the wind on it, but again has the aero and the hydro. And then of course we've got a testing of that there. So you can see there's a lot of different configuration. And as Keith was saying, because we're using PVC pipes, you can sort of Lego the configuration into whatever shape or structure that fits your requirements. And if you move to the next slide, we've done some other field tests that we've been working on in Colorado, here in Colorado as well. And this was of course, in preparation for some of the later deployments that we did in Puerto Rico. But we wanted to test how does it do in colder environments. So as you can see, the top things on the ski trip up to the Mountain Research Station at Niwot Ridge, which has multiple climate zones and Arctic sort of simulated to the climate, high altitude climate zones. You can see how the station performs there and what are some of the issues there. And that's sort of what you'll see here as we've also continued to do some further testing. So we're, again, one of the things that we were looking at too when we were doing this testing is how do we test particularly with the wind, was testing the slip ring and the ability for the whole sensor to essentially turn and keep the wires from getting crossed when everything is spinning around. So that's one of the things we were testing there. And then with some of these tests, we took these tests, and if you go to the next slide, and we started working with some students over in Puerto Rico, and the students were some of which were SOAR students or SCI during the pandemic situation, so we couldn't really travel to Puerto Rico as I wish we could have, but we basically put everything in a box, all of the different pieces that we can, and we shipped all the sensors and everything like that to them, and they got everything together and started putting it all together. And as you can see here in this deployment, they deployed it on the roof of, I believe this is the physics building there, Puerto Rico. And they have a number of other deployments. So if you look at, you can go. So if you look at with lockdowns and whatnot, but approach, which I think for the sort of putting things together. But Puerto Rico, if you look at Puerto Rico in general, if you look at this map here, it shows that Puerto Rico with local contacts with our graduate students there and the NWS, the weather service offices there. So the deployment and budgets are within the grant, and it was this ESIP grant that we received that allowed us to do not only initial work Keith kind of described, but with sending some stations out to Puerto Rico and getting, I think we sent 10 actually out to Puerto Rico because we've expanded it with InCard. So, but under the original ESIP proposal, we're deployed 4 go, but we're expanding that, that course, continued collaboration. We like really working with ESIP, and ESIP has brought on some really exciting and interesting collaborations for us and for this project. We are currently sort of redesigning the station footprint with some new components. We have several small grants to refine and build and deploy more stations, of course, in 2021. There are other partner organizations and universities and whatnot that are deploying the stations very quickly, and they're actually building the stations and making deployments on the stations now. And so some of the indigenous communities, they're building the stations, they're starting to deploy stations on their own. So we're starting to get other universities and schools that are deploying stations. So that's one of the things that, some of the things that we're doing. Next summer, we're gonna have SciPark students that are working on adding a LiDAR and a camera that's gonna be looking at sort of tree swaying. So there's a couple of different projects that we'll be adding to the capabilities of this. So we are actively seeking more grant funding and partnerships, and we'll see where we can make this go. And I think that is the last slide. If we can go to the next one. Yeah, and I think we covered this at the beginning. So if there are any questions, I guess maybe we'll kick it back to Megan.
Yes, thank you so much, Keith and Ag, for that very in-depth presentation. I know we have a number of folks on the line here. We're a fairly small crowd, so if you have a question, feel free to type it into the chat box, but I think we're also small enough that if you just want to unmute and speak up or raise your hand and I can call on you, that would work well. I'll give folks a second to think about what they might want to ask. And maybe while folks are hopefully typing in their questions, I might ask you if you can talk a little bit more about the citizens. So I will save my question. Jeff, why don't you go ahead and ask?
Sure, Jeff Campbell. Perhaps a way to get funding is to say that these sensors would detect air exchange and ventilation in buildings or in classrooms or something along those lines in the current medical context, shall we say.
That's a good point. Yeah. As part of a sort of a similar to smart cities initiative, which is, I think, another sort of interesting opportunity for looking at low-cost microcontrollers and sensors.
Yeah, I would agree. That this would be something that, with the current platform, which was mostly designed for outdoors, there could be adaptations for indoor use, and there are so many sensors out there that that's something that could easily be done. Actually, it'd just be a matter of finding the right sensors for the job. But yeah, that's interesting. That's a very interesting suggestion.
Right. Maybe I'll pop my question in here as others are thinking. You spoke a lot to the educational applications. Can you talk a little bit more about how you hope this can help in the area of citizen science?
Yeah, I mean, so one of the main things, and I think there's a question that just came up. Yeah, one of the main things is, we really do, we're clearly we're advocates of, sort of open source software and, high participation, both with, at all levels within a community, whether you're a developer or whether you're, someone who is analyzing data or contributing to the data or whatever. So I think, trying to infuse more of that thinking into community level citizen science types of activities. We have many ideas and, one area that we've been thinking about has been, how do public libraries and community library services fit into this? I think there's a really interesting opportunity to think about what libraries, in the original data centers were libraries, right? So bringing something of the data center concept more openly, promoted at the public library level would be really interesting to think about as a sort of anchor for the citizen science activities.
Great. So a question in the chat box from Sarah about whether the Climate Change Explorers link is the main one they should use for more info.
I think both of those would work. I think the NCAR link is maybe more active with a few more contributors on it. Is that? I think that would characterize that. But if you're not finding what you're looking for, just reach out to us and we could probably get you in the right direction. We're still trying to shore up some of our, we have a lot of things going on in a bunch of different places. We're trying to, consolidate where we can and make sure that it's not too confusing for people coming from the outside. So thank you.
So a question from Eric Sproles. What is a rough estimate of how much a station would cost? And are the components available under the current logistical limitations?
That's a
yeah. I'm sorry. Go ahead.
That's a good question. There was, when we look at our sensor, there was one sensor that had a shortage because of the current sensor situation, a supply chain situation. But for the most part, all the rest, other than one sensor, everything else have been available. The rough cost on our site, you'll see that there's a breakdown of all of the components for the station, and the station all in costs under $300. Now, of course, you have to print this, you have to print the 3D printed parts and whatnot, but just once you print the 3D printed parts, everything, the station is under $300.
Yeah, and I want to think to that and say that, as Ag mentioned, we've really only had one sensor shortage in the last 12 months, really. And we were able to find an alternate sensor and make some changes accordingly. We've had no problems getting filament for 3D printed, material. So that's been a good thing. Nor do I think we've purchased at least one 3D printer in the last 12 months. And I don't think we've had any shortages on 3D printers. These are lower end printers. So, they're not necessarily flying off the shelves, but they are relatively inexpensive and can be shipped, to your door. So if you are going to do your own printing, right now there don't seem to be any barriers to either printing or getting the raw material for the electronics. One of the microcontroller that we currently use, which can be switched out, it is an ESP32 based microcontroller. So if you wanted to make alterations to the code to accept a different ESP32, you could. That particular microcontroller, we used to have to order that from a company in China, but now they have US distributors. So we've been able to get 2-day shipping for inexpensive, for those sensors, for those microcontrollers in there, about $8.
Yeah, most of the items are available on either Mouser or Seed Studio.
And Adafruit, so we can also, a few things you can get from Adafruit as well.
Yeah, that's a good point.
So a follow-on question from Eric, is this something that could be implemented in a semester-long class?
Is that a university semester or both even same?
I believe Eric is speaking university.
Yep. Yes, this would be a wonderful university, semester-long university course. It'd be pretty awesome. Pretty awesome. And it could be done if you start it with, depending on how you decide to lay it out, right? If you wanted to lay it out in terms of, let me not spend a lot of time on the manufacturing end, and let's say you just had some group that was just manufacturing your parts for you, and you just focused on the deployment and data collection. You could probably get deployment and data collection within the first 3 weeks of the semester, and then do data analysis for the remainder of the semester if you wanted. If you wanted to break it out into sort of these 3 pillars, you could spend, a third of the semester on hardware, a third on software, and a third on data. Or you could flex in the areas that you wanted to focus on. So if you wanted to spend more time on hardware, solving some of the communication problems, or creating some new problems for your students to solve, that would be, you could infuse many new problems into the platform if you want.
Thank you. All right, any other questions? Feel free to raise your hand if you'd rather speak up.
And if I would say on Eric's previous question, if you have any ideas about what you might, we actually have kind of I guess we call it a kind of mock curriculum. It was
we outlined one
like about 8 weeks. Something like that. Yeah.
We did outline one before the shutdown.
So Eric, if you wanted to reach out to either one of us, that'd be wonderful. We'd be happy to share and maybe bounce some ideas off of it.
Go ahead, Bill.
Yes, hi. So a few weeks ago, there was another webinar, I think National Academy of Sciences, where first time I heard the term thermal justice over a city. I was just wondering, it seems like this technology will be very helpful to help document the thermal justice or lack of for that purpose. Yeah.
Absolutely. And I would venture to guess that, again, like I said, the AOT project that I mentioned at the very beginning, they had instrumented some neighborhoods in Chicago. I do not know how much they had expanded that, but something like that where their data was, kind of going into some open repositories, sort of real-time data going into these open repositories. That would also be something to also look into. But yeah, absolutely. Because of the modular nature of the platform, you could literally just put together the radiation shield and stick it on the side of a building, and you've got temperature, VOC, humidity, and pressure just spewing out, constantly. And those are relatively inexpensive, and all their components are, I think what we think Atmos node would probably be not more than $100,
Atmos node I think comes a lot lower. Just the Atmos node by itself is probably, you'd be under $100.
And so if you got clever with the power, you could put a bunch of those in a lot of different places. So that's a very interesting.
And that's for understanding heat island effects and making sure that there are certain issues around that.
And I will add one more thing on when we had mentioned the hardware side of things. For those of you who are maybe new to 3D printing, you may not realize how evolved the 3D printed materials have become, right? And so now we're getting to wood-like materials. There's a filament carbon fiber,
yeah,
and metal-like materials. So, things are getting so sophisticated that even if you thought that the materials that we originally started with were not up to your specs, the wide range of materials that are now available will allow you to do a number of interesting things and place these in lots of interesting places. Yes, so we have been using, this is a question about biodegradable material from Bill again. We are using PLA Plus, which is biodegradable. We have had mixed results, I suppose. The PLA Plus implementations in Colorado have been pretty good. They held up quite well, but we've had some issues with, and we're not really quite sure, but down in Florida, we've got some test units that something's going on either with the combination of the humidity and the heat buildup. Some parts seem to be breaking down kind of rapidly.
Looks like Bill has another question.
Okay, so this is maybe a bit into the future, but so the reason I asked about biodegradable, do you ever see this this technology where you can reduce this down to a very simple sensor that's very cheap, biodegradable, that you can just kind of spread across a terrain, not expecting to recover them for the purpose of fire detection?
Yes, I think Ag, you might want to jump in on there as well.
Yeah, there's for fire detection and sort of drought monitoring, and of course you can add soil sensors to those, and having very, as you mentioned, Bill, having very low cost sensors that you can distribute across an area and sort of fill these sort of data deserts. So of course, in places like the American West, you have fires just like we see every summer, but the ability to have more stations and more observational data that, you're not taking out a $10,000 station when the fire comes across, but rather a couple $100 station would be definitely a better thing, and can actually become part of that fire monitoring and drought monitoring network.
Yeah, and I think the interesting thing is at the current moment, the external shells would probably be the least toxic, most biodegradable component. And if we could get to the point where we're doing 3D printing of the chips themselves, then we could have a choice of non-toxic biodegradable materials at that level as well, right? Because right now the sensors that we're getting are third party, and I venture to guess they are not either biodegradable or not toxic if lamed. But that would be a great project to consider, is if you did your own PCB with materials that were exactly, this is a scenario that Ag and I thought about very early on. If you threw this down into a wildfire and just got measurements until it was overtaken by flames, it'd be a very inexpensive and easy way to do all kinds of interesting things on the research level and on the sort of disaster response level.
Yeah, so if you can detect, some just humidity and temperature, and then give the location, right? That's really all you need.
Yeah.
And then,
And VOCs, that would be interesting as well.
Yeah.
Right. Well, thank you, Bill, for that question. I know wildfire is a hot topic in a number of ESIP's collaboration areas right now, and actually fueling a lot of cross collaboration area connections. So it's nice to see where your work may play into those collaborations. I think since we are getting towards the bottom of the hour, I'm going to go ahead and take the screen share back and wrap us up. Let me grab All right, so I want to say thank you very much to Keith and Ag for speaking today, and also to all of our attendees for joining us and for coming up with such thoughtful questions. I hope that you'll be able to employ something that you learned today and that will continue to keep you thinking. To stay up to date on all things ESIP, I want to encourage you to join the ESIP Monday Update mailing list if you have not yet already done so. You'll see a bit.ly link on the bottom left corner if I'm sharing the proper screen. And finally, I'd like to say that's a great way to stay up to date on the ESIP January meeting planning, which is now just about 80 days away. So time's flying. And also this webinar was recorded. It will be posted on our YouTube channel shortly after. So feel free to share it with anyone who you think might be interested. And please join us again next month for our next installment. And thank you again to our speakers.